different features we should recognise when we see graphs. So if we know what a basic curve looks like, then drawing the curve is going to be a lot easier, because we're basically just transforming a basic curve. So we know straight lines, y equals x being the most basic one. And if we're really unsure, we go, oh look, both of those pronumerals are to the power of 1. We have a linear function. Parabolas, of course, are quadratics. So one of the pronumerals will be to the power of 2, one will be the power of 1. In general, we know, of course, if it's ax squared plus bx plus c. Cubics, oh, it's a 3 instead of a 2. What do you know? So one's to the power of 3, one's to the power of 1. General cubic, ax cubed bx squared plus cx plus d. Now a cubic, oh I didn't draw it there, but remember the basic cubic is the one that inflects at the origin there, but then the other type of cubic is the one where you could have 2 stationary points, so that could be a cubic as well. But anyway, polynomials in general, we spent a fair bit of time looking at polynomials. Hyperbolas, again the most basic one, y equals 1 on x, and then our rectangular one, xy equals 1. So basically if we see a pronumeral in the bottom of a fraction, or we see 2 pronumerals multiplied together, something different's probably happening. The bottom of the fraction one's probably easier to spot it, because you know there's going to be some sort of asymptote, so it's going to sort of bend towards the asymptote, be some sort of hyperbolic function. Exponentials, well, the pronumeral is in the power, or the exponent. Circles, of course, x squared plus y squared is the radius squared, so the coefficients are the same and they're both to the power of 2. And then we saw ellipses where the coefficients are different, but they're both positive. And that of course then brings up another way we could see hyperbolas, and that's where the coefficients were different in sign. Remember, so we had our ax squared minus by squared, that sort of thing. We've also looked at logs now, so that's easy to pick. You see the word log, oh, that could be a log curve. Trig functions, so we've seen the basic sine, cos and tan, and the reciprocal graphs on those, cosec and so on. And then the last set of functions we looked at were the inverse trig functions. So that's the whole family of functions that we've seen so far in this course, and hopefully recognise the basic curve of them and can draw them. The ideas that help us draw it. If we recognise odd and even functions, well, then we're going to have some sort of symmetry. Remember, so the even function has line symmetry about the y-axis. The odd function has rotational symmetry about the origin. Remember the formal definition, odd function negative x is negative function x, and even function negative x is function x. Haven't talked a lot about this, symmetry in the line y equals x. The main thing we talked about with y equals x was when we were talking about inverse functions. Remember, an inverse was a reflection in the line y equals x. Well, if we've got symmetry in the line y equals x, what happens? Well, basically it means we can swap the x and the y and it doesn't change the function. So it is its own inverse, if you like. The simplest one, I suppose, is the basic hyperbola there. I mean, if you swap x and y around, it becomes x equals 1 on y, but it's still the same curve. X cubed plus y cubed equals 1 would be an example of that. This idea of dominance. So if you're not sure what's happening to the curve out at infinity, out of those endpoints of the graph, you want to see which function dominates. Basically, as x gets large, is one of the terms going to dominate? And the one that will dominate will tend to be the steepest. The one that gets steepest the quickest. So in a polynomial, that's why the leading term, remember the idea when we're drawing polynomials, we say it's going to act like the leading term when it starts and finishes. So we just look at that, and that's why, because that one will get steeper quicker than each of the other terms. And so it dominates. Exponentials will dominate pretty much everything, because your exponential starts off shallow, but it gets steep really, really quickly, depending on what the base is. But it's probably going to dominate everything. So in general, as I say, look for the one that gets steepest the quickest. And of course, if you're ever unsure, simply substituting big numbers in. that will tell you what's happening out at infinity. So you might start off substituting 1,000, get an idea for what it's doing, then 10,000, and see, is it getting bigger, is it going towards 0, or maybe some other number. Asymptotes. Our vertical ones, we know bottom of the fraction can't equal 0. That creates the classic vertical asymptote. Horizontal and oblique asymptotes. When we're dealing with polynomials, we talk about if the top of the fraction is a constant, then that fraction can't equal 0. Yes, and if your order of your numerator is greater than or equal to the order of the denominator, we do a polynomial division and then have a look at that. It is possible, remember, for a curve to cross an oblique or a horizontal asymptote. So sometimes have a look and just check whether that can happen. The special limit that we looked at is actually a 2-unit limit. Mind you, you usually don't get tested in 2-unit on it, it's more 3-unit. They like to test this idea. But remember the limit as x is sometimes called the small angle idea. But the limit as x approaches 0 of sine x on x is 1, that idea. Now, a lot of this we don't use calculus with, because we're just drawing sketches, and what the actual turning points are in a lot of these, not that important, but it's still a useful tool when we're trying to get a feel for what's this curve doing. So remember all the ideas for calculus that we looked at, critical points, stationary points, and inflections and so on. So critical points, that was all to do with the first derivative. If the first derivative was equal to 0, we called it a stationary point. Technically, yes, it is a critical point, but when we use the term critical point, we're usually talking about when the derivative is undefined. And so we'll probably get a vertical tangent at that particular point. Stationary points, as I say, stationary points are still technically critical points, but they're the ones when the derivative equals 0, and we get a horizontal tangent. So your two types of critical points, vertical tangents, horizontal tangents. Then your maximum and minimums, and that's where the second derivative came in handy, because we could look at concavity. So if it's stationary, and that one would be concave up, because it's positive, then we know we have a minimum turning point. So if it was the other way around, then we'd have a maximum turning point. Now, if the function's complicated and you don't want to differentiate it for a second time, then just have a look at what's happening with the first derivative either side. Because if you know if it's increasing, stationary, decreasing, maximum turning point, and that might save time in some of the more complicated functions rather than differentiating for a second time. Inflection points. Now we sort of go up a level. Now the second derivative is equal to 0. The quickest way then of confirming it is using the third derivative. The third derivative is not equal to 0. But again, if you've got a difficult function to differentiate, you can test either side with the second derivative and see whether concavity is changing. And horizontal point of inflection. Oh, by the way, technically you can test for inflection points using the first derivative. Because if a curve, right, is going increasing, stationary, increasing, it must be a point of inflection. How else could you do that? I'm going up, stopping, going up. What happened there? Well, it's not a turning point. Must have been an inflection point. So it is actually possible to use the first derivative to test as well. Increasing, decreasing, again, so that's all to do with the first derivative. It tells me whether the curve's going up or the curve's going down. So positive, it's increasing. Negative, it's decreasing. And this idea of implicit differentiation, that came in handy with conics. To save making y the subject, we can just differentiate implicitly. So let's have a look at this one I talked about before there. X cubed plus y cubed equals 1. Let's investigate this a bit further. So we know it's symmetric in the line y equals x, because if we swap x and y around, it doesn't change. Okay, so we know that. So I'll just dot in y equals x there. Okay, I know it's going to be symmetric in that line. I can find the x and the y intercepts quite easily. So now it passes through 1, 0 and 0, 1. Plot those in. Now it makes sense if the y-intercept is 1, of course the x-intercept is 1 as well, because we said symmetry in the line y equals x. This one you might not pick up straight away. It's asymptotic to the line y equals negative x. Now how can I tell that? If I make y the subject, or attempt to make y the subject, I end up with y cubed is equal to 1 minus x squared. Now what that means is y cubed can never equal negative x cubed, which means y can never equal negative x. So that results in y equals negative x being an asymptote in this curve. It's not immediately obvious. Okay, so I'll just dot that one in. So that's going to be an asymptote. Differentiate it implicitly, and we notice here it is, dy dx is minus x squared on y squared. So I know that I'm going to have a stationary point when x equals 0, so that's at the y-intercept, and I'm going to have a vertical tangent when y equals 0, so that's the x-intercept. Okay, let's try and draw that in. Ooh, there we go. X cubed plus y cubed is equal to 1.